Assalamu alaikum, students. Welcome to today's lecture on the topic equation of motion and equilibrium. In this lecture, we will learn how the Newton's second law describes the motion of a particle and how it leads to the condition of equilibrium. We will discuss the equation of motion and apply it to simple inclined plane examples involving fractions. These are the learning objectives. At the end of this lecture, the student will understand the concept of equation of motion. We will explain the condition of equilibrium of a particle, and the student will learn how to resolve forces along a proper direction by applying the equation of motion to simple mechanical system. The student will be able to distinguish between the role of static friction and kinetic friction by studying some problem involving friction. In this course, we are following the book Classical Dynamics of Particles and Systems by Marion and Totten. The starting point in mechanics is the Newton's second law. According to this law, the net force acting on a particle is equal to the rate of change of its momentum. So we can write the force as dp by dt, where this p represents the linear momentum of a particle. And since we are dealing with in classical physics, so the m remains constant during the motion. So then we can write this momentum p as m times, that is the mass times the velocity. So therefore the F equals ma, which is the Newton's second law, but that can be described as m dv by dt since this m is constant during the motion. Now we can rewrite the Newton's second law in terms of this second order differential equation by defining r as the position vector. So since we can express the velocity in terms of the rate of change of the position vector, so this m f, which is the net force acting on a particle, is equal to m, which is the mass times the second time derivative of the position vector. So this is a second order differential equation. So if we want to describe the motion of any particle, uh, we need to know some condition for solving a differential equation. Since the order of this differential equation is 2, so we require two conditions for predicting or describing the motion of a particle whose position vector is r in some later time t. So those conditions are usually defined in terms of the function, which is the position vector, and the first derivative of the position vector, which is the initial velocity. That is, say if we are discussing the free fall, so we need to know the initial height and at which velocity the object is moving or throwing down. So once we have those conditions, the motion can be described at any later time t. If we remember, we have discussed this in the class that this acceleration or the second order differential equation with respect to time of the position vector depends on the nature of the force. Say if the force is constant in time, so that the acceleration will also be constant. That is, if force is constant, acceleration is constant. Say if force is time dependent, then the acceleration will also be time dependent. If say force is position dependent, as we have discussed the case of F is equal to minus kx, so that the acceleration also takes the position dependent form. And also we have discussed the velocity dependent forces that give rise to acceleration, which also changes during the motion, since the force depends upon the velocity of the particle. So in different situation, we have solved this second order differential equation once we have these conditions in advance. So today we are also applying the same concept of the force, but now we have an inclined surface. So before moving forward towards the inclined plane problems, we need to discuss the condition of equilibrium. A particle is said to be in equilibrium when all forces acting on it balances each other. Mathematically, this means that the sigma f equals 0. So once there is no force, there is no acceleration. As I have discussed on the last slide, that if force is position dependent, say, so the acceleration will also be position dependent. So in the same way, if force is 0, acceleration is 0. Under this condition, acceleration becomes 0. This corresponds to two situations. Say either the particle stays at rest or it moves with the constant velocity. So we can say that equilibrium does not always means rest. Simply it means there is no change in velocity because the net force is acting on the particle is 0. So applying those two equations, we have a set of problems involving frictions. That is motion of a block of mass m along an inclined plane. So the first example, if the block slides without friction down a fixed inclined plane with theta equals 30 degree, what is the block's acceleration? So we need to find out the uh, acceleration of the block by, by, by having these information uh, in advance. So since the block slides without friction, so there is no force which opposes the motion as the block slides down. So because the plane is smooth, friction is absent, so we need to first resolve the various forces along the axis. So we have this inclined surface, say this is the x direction, and we have a parallel to the inclined plane, or we can say perpendicular to the inclined plane, which is the y direction, which is parallel to the normal reaction of the surface. So if we resolve the forces, say in this direction there is no motion, so the normal force is balanced out by the f of g cos theta, which is the mg cos of theta. And the other direction, which is along the inclined surface, we have a motion which is only one force, which is mg sine theta. So that is basically responsible for the net force acting on that block of mass m, and that slides down. So having acceleration a, which we need to find out. So if we cut out the m across the equation, we get a is equal to g sine theta, and putting the value of g and from the given data, the value of theta is given as 30 degree. So we can calculate the value of acceleration which this block acquires as it slides down once the angle is 30 degree. So if we see here, this acceleration is smaller than the value of g, since this object is bound, not a free fall object. Say if we make this angle equal to 0, that is just a normal surface, so there will be no acceleration by putting the sign 0 is 0. And if we make this angle as 90 degree, that is almost a vertical surface, so the block will slide down with the value of acceleration equal to g, which will be almost 9.8. So in those two limits, maximum value is of this block can be g, and minimum equal to 0. So this is in between, it is not, the theta is not equal to 0, or this is not equal to 90, in between. So that's why the acceleration is also in between 0 and 9.8. So if you want to calculate the speed of this object after covering a distance, say x naught, by sliding down the inclined plane, so we will use the relation v2as equal to vf square minus vi square. Since the block starts from rest, so that its initial velocity is equal to 0, so vf square is equal to v square and equal to 2ax. And since the last slide we have calculated the value a equal to g sine theta, so if we put a is equal to g sine theta, we can find out the velocity at some later time t by acquiring a distance, say x naught, starting from rest. So we can calculate the later velocity. Now, in this example, the second example, if the coefficient of static friction between the block and the plane in the previous example is mu of s equal to zero point 0.4, at what angle theta will the block start sliding if it is initially at rest? So everything is the same as in the previous example. The block is the same, having mass m, and the theta need to be found out such that now we have a force which opposes the motion in the form of this F. So with this information, now we want to calculate the value of theta such that equilibrium. In the previous example, the perpendicular direction was motionless, so that it was balanced. Normal force is balanced out by the component of the weight perpendicular to the inclined plane. So and along the inclined plane, the block was sliding, so we have a net force. So now we need to find out that condition of inclination over which that equilibrium along the inclined plane will no longer be sustained. So uh, the largest possible value of the static friction F max can be expressed as mu s times the normal reaction, which is the coefficient of static friction. Since the normal force is mg cos of theta, by applying the condition of equilibrium that is in this direction, again this is motionless, so normal force is balanced out by mg cos of theta, and that mg uh, equal to cos of theta can be put in the above equation, so that the friction force can take this form, that is mu times the mg cos of theta. The direction parallel to the inclined surface is now involving a frictional force, so that the component of the weight, which is f of g cos theta, and f of g means mg, mg sine theta is balanced out by the frictional force, unless we make this inclination such that the block is sliding down. So from the second condition of equilibrium, if we see here, everything is known, and can be cut out, like m and m can be cancelled out, the g values can be crossed out, and we will be left only with sine theta equal to mu s times cos theta. So from the sine and cos theta, we can convert it to tangent theta. By putting the value of mu s, we can calculate the value of theta, and that comes out to be 22 degree. So what this 22 degree means, that if you make the theta greater than 22 degree, the block will slide down, because that will be the maximum value of the static friction. And if you make this smaller than the 22 degree for this block of mass m, the block will be in static equilibrium, that is uh, 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 along with the vertical direction. This is motionless. This direction will also be motionless, that is the frictional force will be enough to balance out this component mg sine of theta. If you make this greater than 22 degree, the block will slide down and there will be a net force acting downward. Now, in this third problem, after the block in the previous example begins to slide, the coefficient of kinetic friction becomes mu k, which is equal to 0.3. That is, now the object is in motion, so the coefficient of friction changes from 0.4 to 0.3. We need to find out the acceleration of this block of mass m for an angle theta equal to 30. So remember, this is connected to the previous problem, so everything is the same. And if we see theta is 30, this is greater than 22 degree. So that means the object will slide down. So once it is moving downward along the inclined plane, we need to find out the acceleration as we have calculated in the first example. So the first thing is to resolve the forces along the axis and defining the frictional force in terms of mu k now, because the object will be moving because the angle is 30 degree, which is greater than the 22 degree for the same configuration as we have discussed in the previous example. So again, this direction, the y direction parallel to the y direction is motionless. So the normal reaction is balanced out by the mg cos theta component. And if we define the mu k in terms of this normal reaction force, so this mu k takes the form mu k mg cos of theta by putting the value of n in the above equation. Similarly, now there is a net force acting downward because the angle is 30, so that the net force MA is the difference of the two forces, which is the force component of the force mg sine theta and the frictional force. Because the object is moving downward, so that this force is now greater in magnitude once we are making this angle greater than 22. So we can rearrange this equation to get the value of A, which is the acceleration of this block of mass m while it's sliding down, having a frictional force involving with a coefficient mu k equal to 0.3. So if we put all the values over here, we can calculate the value of acceleration which this block requires for a 30-degree inclination. One can see that this acceleration is 0.24 times the value of g, which is 9.8 meter per second square. Means that is the system is bound and also frictional force is involved, so that the net force is smaller than the mg, which is the weight of the object, so that the acceleration is also comes out to be smaller than g. But the force is constant, so we get a constant acceleration. Now, let us look at the assignment part. In the first question, you are asked to derive the expression for the acceleration and then find the speed after the block moves a distance on a smooth inclined plane. Uh, in the second question, you will use static friction to show the condition for the block to be just about to slide and then calculate the limiting angle. In the third question, you will solve the motion of a block on a rough inclined plane with kinetic friction. So you need to adopt the same configuration as we have discussed in the class or in this lecture. In the fourth question, you will explain the difference between static equilibrium and dynamic equilibrium with examples. So you need to just follow the lecture and draw the free body diagram first and then applying the Newton law. So today we have discussed equation of motion of a particle, and then we applied it to inclined plane motion based on the condition of equilibrium. We have resolved the forces along the various directions, and then using those equations to calculate the required motion parameters of a particle of say block of mass m. I need you to solve these assignment questions carefully and follow the lecture. Thank you very much.